right, hello folks. We are going over homework problems for 1-5 and then we're going to jump into 1-6 notes. So 54 is the first one they said they have a question with. The average water level retention pond in a retention pond is 6.8 feet. Okay, I read that wrong yesterday. For some of you guys I did this with, I thought it said 6 foot 8 inches, which is not true. 6.8 feet. Okay, now then they say that the water level is decreasing at a rate of 3 inches per day. Okay, so if I'm talking about water level as like y, it's decreasing 3 per day, so minus 3x. But plus, what's the starting water level at? If we convert this to inches, 6.8, you take him times 12. 6.8 times 12 is something. Somebody give it to me. Do that exactly so I get the exact decimal.
It's like 80.1.
81.6. Yeah, but when it wants it in feet.
It does want it in feet?
Yes.
Boo.
No.
Boo. So then they, okay.
0.25.
What the heck? All right, whatever. So y equals, I don't care, plus 6.8, and then 3 inches is 1/4 of a foot. So 0.25x. Okay, fine. We'll play by their rules.
So negative 1/4 x.
So, negative 0.25, thank you. Negative 0.25x plus 6.8. I guess if they want it in feet, I didn't read the instructions very well. So this is A. All right, evaluate W20. What does 20 mean if we plug it in for x? 20 days. So 20 days later, how much is left in the pond? If I plug 20 in, 1/4 of a foot per day or whatever times 20 would be minus 5. So negative 5 plus 6.8 is like 1.8. So it has 1.8 feet in a drought. It's going down that much. So it's now only like 1.8 feet tall or deep.
Crazy talk.
Crazy talk. Okay, that was 54.
Yeah, that makes sense.
62, now it makes sense. 62.
Sure, why not?
Caroline adopted a puppy named Dodger from an animal shelter in Chicago and recorded Dodger's weight during the first 2 months. The data in the graph shows Dodger's weight X days after adoption.
Is that a picture of Dodger?
I don't think I believe this. Actually, weight after adoption should probably not be a linear function. It would be more exponential because that's how dogs and people and things in general grow, is more of that nature, but whatever. They're saying it's linear. Whatever.
Wouldn't it like?
Yeah, it should be, well, that's still linear. It should go like that. I'm sorry. I drew the curve the wrong way, but yes, he should go like that. I'm sorry. I drew the curve the wrong way. Yes. It should taper off afterward. But they're saying it's following a linear pattern. Whatever. So 0, 11, and 40, 22, they want A. Use the points to write a linear model. Okay. So we need y2 minus y1. 22 minus 11 over 40 minus 0. You just can't do, Carter, you just can't do bad fractions. Is that the problem? You cannot. Y equals 11 over 40x plus b. Okay, now the nice thing is, Carter, 0, 11. Carter, shh. If you plug 0 and 11 in, Carter, 0 goes here, 11 goes here. What's b going to be? This goes away. So b is, so even though the slope is not nice, the b value is nice. Y equals 11 over 40, x plus 11. There's your function. Okay, interpret the meaning of the slope in this context. So 11 is something and 40 is something. So 11 is the rise, right? What's the rise associated with? Pounds. What's the run associated with? Days. So it is going up 11, I'm going to say up 11 pounds in 40 days. Or if you take 11 and divide by 40, what do you get?
2.75. 2.75.
No. What? 0.275? Okay. If you take 11 and divide it by 40, that is 0.275. So he is increasing 0.275 pounds per 1 day. Does that make sense? So he's going 11 pounds up in 40 days, or he's increasing 0.275 or 0.3 pounds a day ish. Does that make sense? Yeah? I mean, you know. Interpret the meaning of the y-intercept. So he's intersecting the y-axis right here. At 0 days, we're at 11 pounds. What does that mean?
Puppy weighs 11 pounds when adopted.
11 pounds at adoption or at birth. I guess adoption doesn't occur at birth for dogs, right? You have to wait. So 11 pounds on adoption day. That's the y-intercept. If this linear trend continues, which it will not indefinitely, at some point the dog's going to stop gaining weight. That's just the way it works, okay? But if it does, during Dodger's growth period, how long will it take Dodger to reach 90% of his expected full-grown weight of 70 pounds? What in the heck does that even mean?
Take 90% of 7.
90% of 70 is how much?
63.
63. How long will it take him to reach 63 pounds? How do I figure that out?
63 equals.
63 equals 11 over 40x plus 11, right?
Minus the 11.
Minus the 11.
Then divide by
52 equals 11 over 40x. How do I get rid of 11 over 40?
times 40 divided
Times 40 over 11. I can times the reciprocal. So take 52 times 40 and divide by 11, and you get how long?
Got 109 or 89.
189. What's that mean?
I don't know if that's right.
Days. That's how long. Did anybody else get that as well? Yes? Okay. Perfect. All right. E, is the model from part A is it reasonable long term?
No.
No, why not?
Puppy will not grow forever.
Puppy will not grow forever. Just like people. We eventually stop growing.
Even that one kid?
Isn't there?
Even that
Oh,
one
actually,
kid.
I think I saw
There's
him
like a
yesterday.
brain. Like some people have like
A brain tumor in their pituitary gland or pituitary whatever.
Until they die, right? So then they can-
Yeah. It what?
Would he have been at the game yesterday?
Pituitary gland. What?
Would he have been at the game yesterday?
Who?
The kid that you showed us yesterday?
Probably not.
I did see him.
You did really?
I think so. Show me the sister, because I saw the sister.
The sister had really curly hair.
I don't know.
He didn't see
Show
it.
his
He just.
sister.
No! I
You
saw
saw
the
that.
kid, bro. I'm telling you,
You
I
just
saw
call
the
me
kid
bro.
was sitting
Where's
out
she
on the
You just call
bench.
me bro.
I
They're
think-
from Lawrence.
No,
But they wouldn't really have a reason why you.
School here that is like that.
It's not that kid. It ain't that kid.
He's also like 10, probably, right?
Yeah, it was not that
No.
kid.
That kid's not 10. It's a new kid here. I saw him walking in the hall today.
They look very similar.
He's in. We saw him.
I doubt it.
The very last kid.
really curly
hair. We were walking back from the sophomores, and there's all that kid, and then there's that one kid. And I'm like, did he get lost?
Let me see the. Not
see him.
Yeah,
What
Ellie,
class?
who's the new kid then?
No. What class is that? Not
It's
right.
not Brecken.
The Jordan kid.
That's not cute.
All
right. Good?
Beckham?
Is that all? Oh, that's all. There's E. That's the end of it. Okay, what else do you have questions on? Anything? Anything else? Done? Okay, pass them in, please. And let's go to the next thing. Don't look. I'm making you dizzy.
No, Mrs. Vance is first grade. Mrs. Westman is second grade. Mr. Lemeski is third grade. Miss Arkin is fourth grade.
I thought we agreed to not call him Mrs.
Okay.
Buckner.
Mrs. Randall.
That's Miss Randy.
What about people?
Well, do you have a reasoning? Give him a 0 for this
What?
stupid assignment.
Who?
Him.
I'd say something.
Why?
He didn't do it.
Well, I will. Ha. All right. Did you guys pass your papers in?
Yeah.
Please get them to me. Great.
Yeah.
One also thing that I will add, if you don't mind, especially if you're going to turn in papers late or like not on the day that we are doing them on, like if you're gone, would you please put like the section name up at the top of the paper? Like if it's like 1-6 or 1-5, then I don't have to search.
How much are you giving
It's
us
like
the
easier
wrong
for me.
one?
No,
I did
grabbed the
that
wrong
too.
one, Reese.
You grabbed the wrong one.
Yep.
I did that too.
There's two
What?
files back
Was it
there.
1-6?
There was one big
Nope.
pile.
What?
There was one big pile. I grabbed the 1-7.
Two files.
One big.
No,
Bring them
really the
here.
same
They
thing.
got shoved together. I don't know.
I got a 1-6.
I'm
And I got a
sorry.
1-7. So yeah, they got shoved.
They
now.
should be back
No, she
there.
handed me.
I did the same thing.
You can keep him for next time.
Two files. Two files.
No.
There was one pile.
It wasn't two piles.
Two files. Two was
It was one pile.
I screwed that up. I'm
Billy,
sorry.
yeah, we specifically makes Billy look dumb. Two files.
No, me and Billy walked in like right at the same time, and there was one pile.
There was one
There
pile.
was.
It's the same
I
one.
saw it
I
too.
grabbed the right sheet, so.
All right. Anybody else see the 1-6? Sorry, they were in. Like that shouldn't be.
I broke them down. Dang it.
All right. Here we go.
We're not till tomorrow. For 3 days.
That's tomorrow or a couple days from now. Okay. All right. Transformations of graphs. This is gonna be a lot of good review. Let's do this. We have a bunch of little boxes to begin with, but these are what's called the basic functions. A lot of times we call them parent functions.
Yeah.
We have to know where to start from. So parent functions. We're gonna graph these guys. Okay. So a linear function.
Looks like a line.
He looks like a line. I'm gonna make him slanted somehow, but I'm not. I'm gonna slant him like this. That's a linear function. So an example would be like y equals 1/2 x plus 4. I have no idea. That's an example of a linear function. Okay?
Graphing all of them? Or just
We're gonna graph all of them. We're gonna graph all of them.
Wait, hold on.
Okay, that would be an example of a linear
Doing
function.
examples.
Yep, we're doing examples. We're just graphing them. Yep. Nothing else is gonna go in that box. So fill it up. Okay, a constant function. Example of this would be like y equals 4. How do you graph y equals 4?
Where y is always 4.
Where y is always 4. We go straight across horizontal. That's y equals 4. That's a constant function. It's constantly 4, right? Or whatever number it wants to be. Okay, now the identity function is a special type of linear function. Okay, so this, they write it as f of x equals x or y equals x. Okay, he is a linear function, but he's special because he is, how do you graph y equals x?
Well, 4 is 4, 5.
You start at 0, is this like plus 0, and then you go up 1 over 1 or down 1 left 1. This is the identity function. That's a linear function. So it's just a special kind of linear function. Whatever. Okay. All right. Let's go to the other ones. What? Sure. In over there.
Oh, I love quadratic.
Quadratic function.
My favorite.
Okay. All right. Are we ready for the next one? Quadratic. So we have y equals x squared. What does this thing look like? He's a parabola. He's a smiley face parabola. Okay.
Give us an example.
Now, you could have more than just x squared, so you could have like x squared plus 5x plus 6. That's another quadratic function. Or negative 2x squared minus 1. Right? Any of those are quadratic functions as long as the highest power is 2, right? X squared. Okay? Got it? Those are all quadratic functions. What are these numbers, like if x squared just looks like a parabola centered at 0, 0, what's the 5x and the 6, what does all that stuff do to it?
Does the 6 move it up?
The six-
moves
the
it up, and then
6
5 moves it to the left.
Almost, kind of like that. Not specifically like that. In order to move him to the left and right, he would have to look like this. So this would be like 5 to the right, and this would be up 6, right? Yeah. So in this case, no, vertical stretch would be like this guy. We're gonna go over all these, okay? So in order to talk about like the 5 and the 6 specifically, what they're doing to him, we would have to have him in what's called factored form. Right now he's in standard form, so we would have to factor him down, figure out what he looks like this way, and then have him listed like that, right? Okay, we'll get to that. It'll be fine.
We'll do that.
We'll get to that. A few times, not too many. Okay. All right, a cube function or an x to the 3rd power function. This is called I call it cubic. a cubic function. He looks like, do you know?
Is it just
A W.
He looks like a parabola where this half right here has been flipped down. Yeah, like this. Whoop. Oh, not like that. Like this. This is a cubic function. So it's like one half of the parabola and the other half of the other side. So an example of this would be like 2x cubed minus 7x squared plus 4x minus 5. I don't know. Or maybe it's just x cubed plus 12, right? Or anything as long as the highest power is x cubed, right? What does a negative x cubed do? Flips him the other way, so he's going to go downhill. He would go like this, right? If he was negative x cubed. Kind of like a parabola is a smiley or a frowny face, okay? All right, next one is a square root function. Again, these are all just the parent functions. What's a square root function look like? Yeah, he starts here and he goes just that way. He does not have an arrow on this end. He starts at 0, 0. Do you know why he doesn't go this way?
Because you can't have negative.
Right, you can't have a negative inside of a square root. So he just starts there and he goes on forever. Now, if I move him and I say like x minus 5, right? Where the 5 is underneath, then he's going to start at 5. Whoop. He's going to be over 1, 2, 3, 4, 5 and do that, right? But just the square root of x starts at 0, 0 and he jets on forever to the right side, okay? All right, now we got the cube root function. And what does he look like?
You can have it. You can have it.
Yeah, so he goes like this, and he's a little bit flatter than what a square root function is. He's a little bit flatter, and he goes both directions. Why does he go the other direction as well? You can take the cubic root of negative number, right? Like, what's the cubic root of negative 8? Negative 2, right? Because negative 2 times negative 2 times negative 2 is negative 8, right? Okay, so that's how that works, all right? Now, you could have other forms, so like an example of a cubic root function that's going to take this shape. Maybe I could have some like numbers. So 7 times the cubic root of x plus 4 minus 5, right? That's still a cubic root function, but some of the other stuff is going to move him around, right? This is 4 units to the left, 5 units down at a vertical stretch by 7, right? That's what he would do. We're going to learn all of those today. We're going to go over all of them today, all right? So that's still a cubic root function. It will still take this shape. Got it? Okay, absolute value. You know what he looks like, hopefully. What's he look like? He looks like a V at a perfect 45-degree angle unless we do like 2 absolute value of x, which is another example. Or we could have 2 absolute value of x plus 5, I don't know, minus 6. Any of those are absolute value functions. It's going to be a V, but it might be taller, right? Like it might be a steeper one and move to the right or to the left or up or down, whatever, right? But they're all going to look like that V shape. Got it? And the last parent function that we're going to talk about is the reciprocal function. We've done this one before. Do you remember what he is?
L.
He's like the boomerangy guys. So he's an L in this quadrant and an L in this quadrant. He has what's called a vertical asymptote and a horizontal asymptote. Now, you can have like 1 over x plus 4 minus 5. That could be a function. That's a reciprocal function. Do you know how he is moved? Down 5 and to the left 4, right? So down 5 to the left 4, his vertical asymptote and horizontal asymptote would go there, and he would go like this.
Crazy.
Right? So all of those things just move him around. Got it? But the skeleton, if I strip all of the numbers away, he boils down to 1 over x, right? That's what he will come back to. All right, got it? Happy with that? All right, let's talk about some transformations of graphs. Blah, blah, blah. Let's say let's just do, can you put off to the side over here? Some rules.
Probably not.
Let's say we're just going to do all of these as a parent function. We're going to start with the parent function of y equals x squared. Let's just say he's our parent function. What? I'm not going to write a whole lot of stuff. Okay? Let's say I'm trying to shift him up 5, down 7, left 3, and not left 3, that would be right 3. Right 3 and left 4. Okay? And I want to write the rule for that. Okay? Up 5, down 7, right 3, left 4. If I'm starting with my parent function of x squared, what's up 5 going to look like?
Plus 5.
X squared plus 5. That's it. Okay? Y equals x squared plus 5 if you want to put y in there. But if you don't have room, that's fine. Okay? Down 7 is going to be
Minus 5.
x squared minus 7. Okay? All right. What does to the right 3 look like?
Pause first.
Oh, I'll pause. Are we going too fast? What? Minus 3. Yep. And he's x minus 3 squared. So he's inside of the parentheses. That's how you know he's left and right. Okay? The last one, or the left 4, x plus 4. Okay? Notice that he's the opposite sign. So if you want to put a little note here, opposite sign. So like left actually means plus and right actually means minus. Does that make sense?
Yeah.
Okay?
I mean, it doesn't make sense, but
I mean, it doesn't make sense, but that's the way that it goes.
that's how it works.
That's just the way that it works.
Plenty sense.
Right? Okay? All right? Vertical stretch and compression. Let's say I am wanting to, I'm going to go vertical stretch by 7, vertical compression by 4. Okay? Vertical stretch by 7, vertical compression by 4. If my parent function is x squared, what's vertical stretch by 7 look like? 7x squared. What's a vertical compression by, oh, excuse me, that should be not by 4, by 1/4. I'm sorry. You can't compress by 4 because that's still stretching him. Vertical compression by 1/4, he will be y equals 1/4 x squared. Now, how can you tell just by looking at the number whether he's a stretch or compression?
Well, no. If
Less
it's under
than,
one,
no.
Greater than 1 equals stretch. Less than 1 equals compression. Does that make sense? If it's a number that's bigger than 1, it's going to make it taller, right? Like I'm doubling your height, you're going to be taller. If I'm halving your height, like making you half the height that you were before, that's going to be a number smaller than 1. It's going to be making you shorter. Vertical compression, okay? What if the number is equal to 1?
No change. No change.
Equal to 1 equals no change. So if you want to write that down, you can. You don't have to. Okay? All right. Let's go into the other one. You've got another little box. Over here, horizontal stretch and compression. We'll make him real small. If you have a, let's say, a horizontal stretch by 5 and a horizontal compression by 1/8. Okay, again, the rules apply. It's a stretch if it's a number bigger than whatever, if it's a compression, if it's a number smaller than 1, right? So if I have x squared, if that's my parent function, what does this thing look like?
We put it on the outside and then.
So he'll be in the parentheses and he'll be squared, but when you do a horizontal stretch or compression, you have to use the reciprocal. Okay, what's the reciprocal of 5? 1/5. Okay, so I'm going to put 1/5 in parentheses, so he'll be 1/5 x, that whole thing to the second power. All right, you have to flip him. All right, what is a horizontal compression by 1/8?
That doesn't make it.
I'll hold on. I'll answer your question here in a second. He will be 8, and he will be to the, or 8x to the second power. Okay, how does that make sense?
I mean, because it makes sense. Yeah.
How does that make sense?
Well, I just did
No, you're fine. You're fine.
Stretching, when you're stretching 1/5 means that it's gonna go
Yeah.
over more, so you're stretching that horizontally.
Yeah. So right. Yeah, exactly what Connor's doing a good job of explaining. So when you're I'm gonna go off of what Jack just said. If you are horizontally up, if you're vertically compressing, like I think of a peanut butter and jelly sandwich. If I take a peanut butter and jelly sandwich in my hand and I'm vertically compressing, which means I'm making him shorter, he's going to horizontally expand. So a horizontal stretch, which is this guy right here, is going to look similar to a vertical compression, right? So the 1/5 represents a vertical compression, okay? Now, actually though, if you really want to talk about what numbers they are, if I go ahead and I square this, 1/5 squared would be 1/25 x squared. If I got rid of the parentheses, it would look like that, true? Okay, So a horizontal stretch by 5 is actually going to be a vertical compression by 1/25 instead of 1/5. Does that make sense? Because you're squaring it for this problem. Okay? Confusing? A little bit? Okay? Because you're squaring it, the horizontal stretch by 5, when you square it, is going to be 1/25 if you change it to a vertical compression, right? If you get it out of the parentheses. Weird stuff. Now, if I was doing to the third power, if this was x to the third power, you know what would happen? A horizontal stretch by 5 would be a vertical compression by 1/125, because I would take that to the third power. Does that make sense? Lots of weird stuff. Okay, anyway, you don't have to know that. You don't have to know that. If that snowed you, that's okay. All right, when you are reflecting, blah, 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 the negative goes on the outside of parentheses if you are going over the x-axis. So this is the x-axis reflection. This is the y-axis reflection. So if I am taking my, and the negative goes inside for the y-axis. So if I have my parent function as x squared, here's the difference. Over the x-axis will look like this. Over the y-axis looks like this. Okay, now, real quick though, this bottom one, if you take negative x and square it, meaning negative x times negative x, what do you get? Positive x squared. So you mean to tell me that if I reflect it across the y-axis, it doesn't change it? You mean to tell me if I take a parabola and reflect it across the y-axis, it's not going to change it?
Well, it depends on where
Is that true?
Yeah.
If it's just, yes. If you have numbers in there, it will not. But if we're just doing x squared and I reflect him across the y-axis, he doesn't change him, right?
Yeah.
If there's numbers in there, it's a different story. But if it's just x squared, that's why when we square this negative, which is across the y-axis, it returns back to the original function because it, right? It doesn't change it if you've reflected across the y-axis if it's just x squared. Got it? That's why. If that was confusing, don't listen to that. Okay? All right. Let's do some problems. On your homework assignment, you don't have to graph anything. You just have to list like what is being done. What time do we get out of here? Somebody look over there. 40?
Yes, 42.
Okay. All right. Use the translation to graph the given function. One thing. Let's do the parent, and then let's do the transformation. So,
Let's not do the parent.
well, I have to identify the parent before I can like look at the number part of it. So what's the parent? The parent is y equals absolute value of x. Okay. What's the minus 3 do?
Makes it down 3.
Down 3. There you go.
It's a V at negative 3.
It's a V down 3. So here he looks like this, and he's doing one of these. You don't have to graph this on your homework assignment, but we're going to graph it on here. So this is what he looks like. The original guy would just be this. But A is going to look like that. Okay? B. Oh, now they gave us, what's the parent for this guy? Y equals x to the third.
It's going to be
The transformation is?
to the left.
Nope. Up to. Okay? So now he's going to look like this. Because he's x to the third power, and he'll be up to. Yep. We got lots of graphs going on. So this is B. The original guy looks like this.
Do we have to have the original graph?
No. You don't have to graph it all on your homework.
Oh, okay.
I'm just doing this for you.
Oh, I'm doing it.
Okay?
Why did I use that?
All right? What? Yes. There you go. Okay? Happy with that?
No,
Let's go down to the next one. I'll keep that one kind of on the screen.
I'm kidding.
What's the parent function for example 2? Y equals x squared. Okay, the 3 is squared, not cubed. The 3 is inside of parentheses. What's the plus 3 do? To the left 3, because plus means left. So I'm going to the left 3. So I have a parabola that's a left 3, and he goes like this. Just like that. Got it?
All I have to do is just do the parent and the transformation.
Yep. So on your homework assignment, you don't have to graph.
Do we not go to the parent?
What?
Do we have to do the parent?
Technically no, but yeah, it helps. Whatever you want to do. So technically you don't even have to do the parent. I always put the parent down. Example 3, what's the parent?
The square root of x.
Y equals the square root of x. Okay, now how many things are being done here?
2.
Two things. Okay, now let's go in order. We've talked about this before?
Let's just say down 2.
Yeah, have we talked about the order that you have to go in? if I were to, so we have to decide, is the -3 happening first or is the -2 happening first?
-3.
If I were to plug a number in for x, here's how you decide. If I was to plug a number in for x, would I subtract 3 from it or would I subtract the 2 from it? You would do the 3 first. So the -3 is going to go first. That moves him to the
Why would that matter?
right 3. And then this one is moving him down 2. Now, does it matter in this case if I go right 3 and then down 2 or down 2 and then right 3? No, but here's when it matters. Let's say I shift something up 2. So if I'm starting here at 0 and I'm going up 2 and then over the x-axis versus over the x-axis, over x and then up 2. Okay, let's talk about that.
Yeah, that's a little different.
Let's start at a different point other than that point. Let's start right here. Okay, if I have this dot and I'm going up 2, 1, 2, he's now here and then I reflect him over the x-axis, he's going to be down here. Versus if I take this guy and I reflect him over the x-axis first and then I go up 2, he's going to end up here. Does that make sense? So sometimes the order matters, sometimes it doesn't. In this case, we're just doing transformations, right? But if you have any combinations of stretches and compressions or reflections, you need to make sure you go in order. If you're only doing translations, it won't matter. But stretches and compressions, so just get into the habit of always doing the correct order, okay? Because if you ever have stretches and compressions or reflections, it will matter the order that you go in. Got it? Okay, go ahead and do example 4. Blah, blah, blah. My original function is the absolute value. They want us to graph it. We'll graph it. Sure.
Just V.
He's just a V. Okay. And then 2 to the x power. What's that doing?
Making it steeper.
Making it steeper. He's a vertical stretch by 2. Okay. He's making it steeper. So rather than going up 1 over 1, up 1 over 1, I'm going up 2 over 1, up 2 over 1, up 2 over 1. And he's looking like that. Okay. Okay. Now what's the other one do?
Compression.
He's a vertical compression by 1/2. So instead of going up 2 over 1 or up 1 over 1, I'm going up 1 over 2. Up 1 over 2. He's short and fat. Okay, because a vertical stretch a lot of times looks like a horizontal compression. That's the way that it works. Us short people are short and fat. That's just the way that it works. If you took my body weight but put it on a 6 foot tall person, they'd be skinny as a stick. But because I'm short,
Stop.
it looks different. I mean, that's just the way it works. That's just the way it works. That's science. That's science. Okay. Example 5. I guess if you have some like this on your homework assignment, you will have to graph these. Okay. I don't know if I do.
You lied. Why?
Well, because you will, because there's no parent function. They're giving you a nonsense function that's already graphed. They're giving you a nonsense function that's already graphed, and they are wanting you to do this to it. Okay? So the 2 here is inside of parentheses. What does that thing do? He is a horizontal compression by 1/2, because we have to use the reciprocal, right? He's a horizontal compression by 1/2. Okay, so I'm going to compress this thing horizontally by 1/2. So I take this nonsense function. I have 3 points, and I'm compressing them horizontally by 1/2. The origin, or the place that I'm compressing him horizontally is this way, right? I'm doing it this way. So I'm doing it toward the x-axis. I'm making everything, the y-axis. I'm making everything closer to this pole right here. So all of this stuff is getting smashed in this way. Half the distance what it was before. Does that make sense? So looking in relationship to the y-axis, this guy is 2 units away.
So 1 unit.
So now he's going to be right here at 1 unit away. Does that make sense? He's half the distance what he was before. Okay. This one over here was 4 units away. So now he's going to be 2 units away. This one was 1 unit away on the other side. So he's going to look like this. And does he look like he's been smashed half in?
Yeah, I guess.
Yeah. Does that make sense? Everything's squished toward the x-axis, okay? If you're doing vertical, it's going to be toward the x-axis. Did I say y-axis? X-axis. He's going to be squished this way, okay? All right, this one, what does the 1/2 like this do?
Stretch.
That's a horizontal stretch by
2.
2. So I'm going to go back to my black guy, and he is 2 units away,
Make him 4.
and now I'm going to make him 4 units away. The bottom one is 4 units away, and I'm going to make him 8 units away, and 2 units away, and 4 units away. So now he is like this, and I have made him fatter. Was that a lot?
That's the easiest thing we've done all day.
Hey, perfect. A lot of people look at this notation though and they get confused. That's just saying we don't actually have a function for this because it's just 3 points, right? But that's what they're asking you to do. Got it? All right, let's stop there. Should we do that? We'll finish the rest tomorrow and we won't have very much to do, so you'll be good. Okay? You can get quite a bit done though, I think, of the homework assignment probably. Oh, homework problems. If you are just tuning in or like in here, there's the homework problems.
You can complete the homework.
You can complete the homework? Yeah.
Yeah.
You probably can get a decent ways.
No, you can like go
Do all
the way
of
to
it.
7.
Nice. Very nice.
Hey.
Oh, who said earlier that today feels like Thursday?
Me.
Who was that?
Me.
Eli?
Ellie.
I'm sitting here like, oh, tomorrow will be a good Friday because we'll have only 3 problems left. What did you do to me?
No, I for real because we have practice.
What did you
Sunday.
do to me?
It's because we have practice Sunday. That's why I feel like
Oh, yeah. And you had morning practice today, right?
there's a game tomorrow.
And you have a game tomorrow. See? I don't know what you did, but that doesn't affect me at all. So you guys just got me in the same boat as you. I don't know why. Okay, goodbye, people watching this.